Hello, everyone, and welcome back. We're picking up our video where we left off on tree traversals. So we've already done binary search tree inserts, searches, and deletes, successors, minimums, maximums. Let's talk about traversing our entire tree. So a tree traversal is an operation that is basically us visiting every single node in the tree exactly once in some kind of an order. This concept of traversal applies to trees and graphs, not just binary search trees. So we'll see traversals in other types of trees that we're going to look at, as well as graphs later in the course. Now, I claimed that the structure of a binary search tree would allow us to get a traversal, not just an efficient traversal. I don't like this says for efficient traversal. Let's say an efficient sorted or ordered traversal compared to a hash table. So how is it exactly that we want to traverse a tree so that we can do this? So there's three different ways that we typically traverse a tree. The first way is pre-order. The next way is called the post order, and then the in order. Now, these line up very similar to what we saw when it came to prefix notation, postfix notation, and infix notation. And infix notation is the one that we're used to seeing. So using that, we can sort of extrapolate that the in order traversal would be our sorted or ordered traversal. So the purpose of a tree traversal is typically to perform some kind of an operation on each node. For our basic example, we could be talking about just printing the data in each node, but it's entirely possible that we want to do other things like finding pathways through our nodes, trying to travel through them in a specific amount of time. Really lots of interesting graphing problems come down to different ways of traversing graphs. So the pre-post and in-order terminology, as I said, is very similar to what we saw before with our arithmetic notation of when we used our operator versus our operands. So pre-order, post-order, and in-order are specifically referring to when we act on the current node. So do we act on the current node before we act on the children, after we act on the children, or in between acting on the children? So pre-order means pre, so before. So we'd first do the action, whatever it might be, that performs some operation. We would perform that operation on ourselves and then our left and right children. Post order would have us perform that operation on our left and right children before we did ourselves. We'd be the last one. And then the in order traversal would be performing the operation first on our left child, then on ourselves, then on our right child. This is a very naturally recursive problem, and we're going to see some really neat magic as to how exactly this works. So let's start with a pre-order traversal. And we're going to talk about this act on a current node. And let's just assume for a moment in time that this action that we're talking about is the print line of our current node's data, just to make our life easier. But it really could be any kind of action. So in a pre-order traversal, we act on the current node first, and then we recursively perform a pre-order traversal on the left subtree. And that will keep happening all the way down until we hit the bottom of it. We'll backtrack back up, and we will recursively perform a pre-order traversal on the right subtree. In this scenario, the current node is always going to be acted on first, and that's why it's called pre-order. So let's look at a tree and see what this looks like. If we know that we want to print each node out in its pre-order, oh, my whole thing just twisted there. In its pre-order ordering, pre-order means cur, left, and then right. So what, oops, I can do that on two separate lines. So what does that actually mean if the action we were doing is a print? Well, we start at the root. So our root would be cur, and we would print out 18. And then we would go to the left. And this is like a recursive call. At this point in time, there is a method call on our runtime stack that sort of signifies the fact that we are not finished running 18's methods because we haven't gone down the right side, but it's kind of holding our place so that we can go to 12. And then we're going to run this whole thing on 12. So then we're going to print out 12, and we're going to go down the left subtree. And then we're going to print out 6. We're going to go down the left subtree. We're going to print out 2, and we're going to go down the left subtree. Oh, but it's null. So at this point in time, we would stop and we would go down the right subtree. Here at the right subtree, we would print ourselves out and try to go down the left. There is no left. We'd try to go down the right. There is no right. So what happens is we're going to come right back up. We do our backtracking. We finish with that call to 3 on the stack. We move back up to 2. 2 is completed its right call. So that also gets pulled off the stack and the backtrack comes back up to here. We go back to where we called 6.left. And we are now finished with that call. So we now know we're going to go and do 6.right. So we come down here and we do the same thing on the value that's here. We're going to do 9. Then 9 is going to try and call left. There is no left. We're going to try to call right. There is no right. So what happens is we backtrack back up. 6 is now finished running. What happens is we're going to go over here to 12. We've now completed 12's cur, 12's left. We need to do 12's right. So we're going to go down here to 15. 15 is going to print out. We're going to try to go to the left. We can't, there's nothing there. So we go to the right. 17 prints out. We try to go to the left. There's a value there. We get 16. 16, try to go to the left. We can't, there's nothing there. Try to go to the right. We can't, there's nothing there. So we come back up, backtrack out up to 17. Here we try to go left. There's nothing, or pardon me, we try to go right. There's nothing to the right, so we can't. So instead we backtrack back up. 15 just completed running. It's 15.right, so it will backtrack back up. 12 has finished running. It's 12.right. It will backtrack back up. 18 will now have finished running its 18.left call. So now we can move on to the 18.right call. 18.right call brings us down to here where we will call 27. 27.left brings us to here where we call cur, so 25. 25.left pulls us to here, 21. 21's dot left will pull us here to 20. 20's dot left gives us a null, so we can't do it. 20's dot right gives us a null, so we can't do it. So we're going to go ahead and backtrack back up. 21's right is going to give us a null. We can't do it, so we backtrack back up. 25's right is going to give us a null, and we can't do it, so we backtrack back up. 27's right takes us over here, and we can do it. So we call 36, and we're going to call 36.left. 36.left is going to bring us over here. We print out 32, and I am going to run out of space. Let me move all of this over. There are a lot of values in this tree. 32.left, can't do it, it's null. 32.right, can't do it, it's null. So we backtrack back up, and we go down to 39. 39 is going to print. 39.left is not a thing, so we come over here. 39.right takes us to 40. We try to do 40.right, or pardon me, .left. There's nothing there, we can't do it. We try to do 40.right, there's nothing there, so we can't do it. So we backtrack back up. We've now finished running 39's right, so we backtrack back up. We're now finished running 36's right, so we backtrack back up. We're now done running 27's right, so we backtrack back up. We're now done running 18's right, and now our program is completed. This is a pre-order traversal. You will see that we printed ourselves before we went down our left subtree. You will notice that every single node has the arrow pointing down away from it, as well as an arrow coming into it. And this is representative of the runtime stack and how the calls are going on and off the stack. Every arrow coming out is like a call away from that node. And every time the arrow comes back up, that is us coming back up to finish our call of that node on the runtime stack. So every single node here, leaf nodes only have like one coming in and one going out, but all other nodes, these internal nodes, have like 2 of each, because we have, for example, here is our printing of 18, our recursive call to the left. And once all of the left is done, we have to come out of that and come back up. which will allow us to go over here to the right. And then once our entire right is done, we come back up and then we've completed our print, our left, and our right. And therefore, we have completed that entire node. And that's true for every single level, every single node, how we go through it. Cur, left, right. We can see this also in this picture here. This picture is denoting the order in which the values print rather than the calls on the runtime stack. Mine with the arrows is more representative of the calls on the runtime stack. Now, a post-order traversal would be exactly the same, except instead of acting first, you'll notice that we're acting last. So what does this mean? It means we're going to go all the way to the left, and then we're going to try to go all the way to the right. And once we've done that, then we act on ourselves. So again, if we look at that here, I'm going to take a little bit of a shortcut here because I did just go through that whole thing. But we know that we're going to say, let's go left. Is there a left? Let's go left. Is there a left? Let's go left. Is there a left? No. Is there a right? Yeah, let's do it. Is there a left? No. Is there a right? No. Now act on ourselves. We're going to get 3. Then we're going to come back up. We've already done our action of our left and right. So now we can print ourselves. Here we haven't done the action on the right. So we go to the right. We're going to print 9. We've done the action on the left and right now. So we can print 6. The colors no longer matter. I'm not doing a good job of it. Here we've already finished the entire left subtree of 12. So now we can go over here and do the entire right subtree of 12. We try to go left, there's nothing there. We try to go right, we can. We try to go left, we can. No left or right, we're going to print 16. We try to go right, we can't on 17. Once we're done, we'll have done the entire subtree on 15. So 15 can now be acted on. We come back up, we finished the right subtree. 12 is now acted on. We come back up to 18 and do the entire thing on the right subtree. Just do it like this. And then the very last thing to print would be 18 in this scenario. So in the in this pre-order, the very first thing we did was print ourselves. So 18 was the very first thing to print. But over here, because we're always doing the operation on ourselves last, 18 is going to be the last thing to print in this scenario. If I told you I had a post-order traversal of data that looked something like this, and that was my post-order traversal, you could reverse engineer this back into a binary search tree if this was a post-order traversal. Okay. Once again, this shows the order in which the values are printed. So the very first value that got printed is here. Here, you can see the order in which everything is getting printed appropriately. Once we finish printing out 12, we have to go back up and find our way all the way down to 20, which is why there's this awkward line that's going between 12 and 20. That's because after 12 prints, 20 would be the next thing that prints, then 21, then 25. Then we would go from 25 all the way down here to 32. From here, we'd go all the way down here to 40, and then we'd backtrack our way all the way back up. This is post order. All children nodes are acted on before their parent. The last one and the most common one is, of course, our in-order traversal. When we do our in-order traversal, we're actually going to be getting an ordered action. So ordered in terms of chronological order. So first we do our left child, then we act on ourselves, then our right child. Pre-order, this came first. Post-order, this came last. Last, in order, it comes in the middle. That makes perfect sense. So the current node is always acted on in between its left and right subtrees. This is our in-order traversal. So to traverse this tree, we follow the same pattern here where we go, is there left, go left, is there left, go left, is there left, go left, is there left, no, print ourselves. So this gets printed first. Then we go right. Can we go left? No. Print ourselves. Can we go right? No. Backtrack. Backtrack. Print ourselves. Can we go right? Yes. Can we go left? No. Print ourselves. Can we go right? No. Backtrack, backtrack, print ourselves. So we've got 2, 3, 6, 9, 12. Can we go right now? Yes. Can we go left? No. Print ourselves. Can we go right? Yes. Can we go left? Yes. Can we go left? No. Print ourselves. Can we go right? No. Backtrack. Print ourselves. Can we go right? No. Backtrack. We're completing our right side. We backtrack. We backtrack. We can now act on ourselves up here, 18. You'll notice that we are getting an ascending order. Whoa, an ascending order traversal of our nodes. Go to the right. Can we go left? Yes, left, yes, left, yes, left, no. Print ourselves. Go back up, print ourselves. Can we go right? No. Go back up, print ourselves. Can we go right? No. Print ourselves. Go back up. Can we go right? Yes. Can we go left? Yes. Can we go left? No. Print ourselves. Can we go right? No. Backtrack. Print ourselves. Can we go right? Yes. Can we go left? No. Print ourselves. Can we go right? Yes. Can we go left? No. Print ourselves. Can we go right? No. Backtrack. We've completed this one. Backtrack. We've completed this one. Backtrack. We've completed this one. Backtrack. We have finished our traversal. And as we can see, we get an ordered output. Again, this blue line is indicative of the order in which we printed stuff, not the call stack. Mine is indicative of the call stack. If you follow my arrows, starting from the root all the way down, you both get the order in which things are printing and the order in which things are being called. All right. Typically, where is it? It's in here. It's usually in here somewhere. Perhaps I missed it. Hold on. Here it is. Yeah, our pre-order traversal is typically called our depth first search, where we are always looking at ourselves before we move further down. Look at ourselves, move further down. Look at ourselves, move further down. Look at ourselves, move further down. So we go as deep as we can, and then we're down the left here, and then we go as deep as we can down the right. Deep as we can down the left, deep as we can down the right. Deep as we can down the left, deep as we can down the right, and so on and so forth. This is called a depth first search traversal and is quite common way of moving through data when we're looking for values or doing other types of algorithms that you'll see in 2080 and beyond. Maybe a little bit actually at the end of the term in graphs as well. I want to find that term depth first search. Okay. To finish off this conversation, let's just define some more terms that we're going to need for our algorithmic complexity of binary search trees. The height of a tree is the number of edges along its longest edge. So if we go along its longest path, pardon me. So the furthest, the distance from the root to the furthest leaf dictates our height. Some sources might use nodes instead of edges. We're going to use edges. So in this tree, we have a height of 3 down that path. We have a height of 3 down that path. We have a height of 3 down that path. And we have a height of 2 down that path. We're going to take the maximum because we're looking for the longest path. So our height for this tree is going to be 3, since that is the longest path that exists. There is a path that is shorter, but that does not dictate our height. We're always going to be using the longest path. That's super important. Longest. Okay. A full binary tree is one in which every single row has the maximum number of nodes, which means every single row that exists, every node is 2 children, except for, of course, the leaf node at the bottom. So you'll notice that this row, there's 2 children. Every single node on this row has 2 children. Every single node on this row has 2 children. And then every single node on this row is a leaf. I hate that that doesn't always work and make a nice rectangle. Okay, if we have a full binary tree, we do have some math that we can perform on it. If we have a full binary tree, that means that everything on that final row is a leaf node. It also means that every single sort of path will meet that same height requirement. So we can see here that the longest path from root to leaf for every single node is 3. So they're all 3, making our height 3. A full tree with height 3 will have 2 to the h plus 1 minus 1 nodes. So if it's a full tree, this level 1, I guess we'll say, has 1 node. We're going to actually call this like level 0. This is level 1. This is level 2. And this is level 3. What are we actually doing here? Well, this is like level 0 is full, so we're going to say 2 to the 0. Level 2 is full. Sorry, level 1 is full, 2 to the 1. Level 2 is full, so we have 2 to the 2. And level 3 is full, 2 to the 3. You'll notice that 2 to the 0 evaluates to 1, and that's how many nodes we have here. 2 to the 1 evaluates to 2, and that's how many nodes we have on that level. 2 to the 2 will evaluate to 4, which is how many nodes we have on that level. And 2 to the 3 will evaluate to 8, which is how many nodes we have on that level. And so when we take each of these levels and we binary, right, that's right where we got that 2 from, if we sum up these numbers, we will actually get 15. So we can see that using like our understanding of binary number systems, but we can also understand that if I tell you that we have a height of 3, that's why we're counting the node levels starting at 0, 1, 2, 3. We can also say 2 to the h plus 1 minus 1 is going to give us 2 to the 4 minus 1, which is 16 minus 1, which is 15. And this is exactly the same as counting by the nodes instead. A full tree where we have a height 3 means we have a level 0 of nodes, a level 1 of nodes, a level 2 of nodes, and a level 3 of nodes. When we add that up, we also get that 15. All right, so if we let n be the number of nodes in a binary search tree and we let h be the height of the tree, then our insert, our search, and our delete operations that all start at the root and proceed from one row to the next until at worst, we reach some kind of a leaf. So our worst case is the number of pointers that each of these operations needs to follow, matching up to that height of the tree. So we know that our insert, our search, and our delete are all going to be O of H operations, meaning O of H operations actually does mean with respect to the height of our tree. So we saw in a full tree how that looks here. If we have a full tree of 15 nodes, we can see that we ended up with 2 to the h plus 1 minus 1, giving us that 15. How does this actually connect back to our data? Well, if we have a full tree of 15 nodes, we can do some very, very nifty logarithm math, which will allow us in log base 2 to connect our height back to our tree. So here we have 2 to the 4 minus 1 right here, right? So if we have a height of 3, we know that that means that the number of nodes is going to be 2 to the 4 minus 1. We just saw that up here. Sorry, that's kind of messy. Now, if I take the log, 2 to the 4 minus 1 is equivalent to saying 2 to the 4 minus 2 to the 0, as we just saw in my other way of showing you this. If I take the log of both of those, oops. If we take a log base 2 of both of those, we're actually going to end up with 4 minus, actually don't need to take the log of both. I can just take the log of the 1 and leave this as 1 for a second to get our height back, right? So if we leave that as it is, there's no reason to change it over. We can do log base 2 of 2 to the 4. our number of nodes we said was 15. This was 15. Let me do this. Let me write it all out instead of being so quick with my pen there. Because what we'll actually do is say 2 to the 4 is equal to 16. I'm just moving that over. And now I can take my log base 2 of both sides. Log base 2 of 2 to the 4 is equal to log base 2 of 16. And what are we going to end up with? We're going to end up with 4 is equal to 4, obviously, there. So what we see is that our time complexity in terms of n is directly related to our height. If we were to put this back in number of nodes, we could say n is equal to 2 to the 4 minus 1. And what do we actually end up with when we do that? N plus 1 is equal to 2 to the 4. And if we take a log of that n plus of n plus the log of 1 is equal to the log of 2 to the 4. In this scenario, what we'll end up seeing is that our log base n is equal, I guess I could have left the minus 1 over there, to 4 minus 1. Guess I could have left that minus 1 over there. Sometimes things are a little kooky. We can leave it over there, and we can see that log n is going to be equal to 3. So what do we actually end up seeing? It doesn't, the math here is actually a little bit more like rounding-ish, but that's okay. What we actually end up seeing here is how we can relate our big O of H into, if we would have rounded up, if I would have actually taken a ceiling appropriately for what would have needed to be over here, when I would have taken the log of that, is we would see that we'd be able to relate our H directly back to our log n. Now, I kind of fudge that up a little bit, but honestly, I'm okay with that, and I'm not going to change it because your assignment is going to actually ask you about this. And so leaving it a little bit fudged up, hopefully I have drawn enough of a connection between H and the number of nodes to allow you to comfortably work through that in a much more elegant way. But we can sort of see the pieces there between looking at the binary tree up here, how H relates to it, and getting log in there. I kind of fudged up the math a little bit in my explanation of it, but I don't plan to fix that because I would like to leave it up to you to determine the more elegant way of writing that out. Now, let's suppose, let's just talk about time complexity very quickly to wrap this up. If we suppose that n nodes, here we go, we can see it more clearly down here. If we suppose that n nodes are arranged into a full binary tree or as close as we can possibly get to it, we know that if our height is 3, our number of nodes is going to be 15, right? So if our tree has a height of h, then the number of nodes is going to be 2 to the h plus 1 minus 1, which, as my very awful math just showed, we end up with h being equal to this wonky function right here, because 2 to the h plus 1, if we take the log base 2 of that, let's actually, can I deconstruct this math? Ugh, I want to do it, but I'm not going to. I will do it later. If you take the log here and the log there, etc., we can make it work. But I'm not going to do it because the assignment literally asks you for this. So I'm not going to do it. I have to restrain myself, but we can see how we can take the logs to reach a place where we're going to end up with something that looks effectively like this. And we know that we don't care about this and we don't care about this because those are just constants. And log base 2 of n plus 1 minus 1 is 100% in O of log n. And if you don't believe me, this is something that you now know how to prove. You can use there exists an m greater than 0. Pardon me. there exists an n naught greater than 0, that for all n greater than our n naught, log base 2 of n plus 1 minus 1 will be less than or equal to m times log n, log base 2 of n. You know how to do this. You can formally prove why we know this to be true very simply. I was doing it quite hand wavy before, but we can prove it with actual real math if we want to. Okay, so this is our best case scenario here. I know it says big O. Really, we're talking about big omega, really. And by that same logic, it ends up with in a full tree. So if we know we have the best case looking tree, big O, big omega, theta, we're going to end up with a full binary tree, a runtime of a height of log n. Now, how does this relate to a worst case tree orientation? So we're talking about the best case orientation. And in the best case orientation, what is the worst case height? That's what that originally was. Our best case orientation is a full binary tree, which results in a worst case height of log n. So the worst that we could possibly have there is log n. Now, if we have a worst case orientation, how does that affect our worst case time complexity? So this is also a binary tree. This is a much worse orientation. Clearly, because here n is our number of nodes, and our height here, right, we're counting edges, is going to be h is going to be n minus 1. And if h is n minus 1, and we do this same math as we wanted to do prior, where h was equal to this fun math, right? We can do that same thing over here. And we can now realize that if h is equal to n minus 1, we know that n minus 1 is in big O of n. So in a worst case configuration, our height is going to be in O of n. And in a best case tree configuration, our height was in O of log n. That's what we just sort of saw there. This is a problem, obviously, because we care about worst case scenarios, and we need to consider our worst case configuration when considering our worst case scenarios. It'd be nice if we could think about our best case configuration, but we can't use that as our default for analysis. Our true worst case has to be worst case configuration, worst case height, worst case time complexity, which means that since our big O notation represents our worst case, we technically have to say that our insert, our search, and our delete operations are still all big O of n with a binary search tree. Because in our worst case scenario, our worst case height will be the height n minus 1, right? It's a linear linked list. But these could be potentially worst case log n if we can find a way to force our tree to look full and not like a stick. And so we're going to leave it at that, because our next lecture set is going to be us actually doing this. We're going to find a way. Can we potentially find a way to force a best case tree configuration, which would then allow us to say that our height will always be in big O of log n? And the answer is yes. And that's going to be a balanced tree. And that's what we're going to look at in our next set of lectures. Okay, so this is where we're sort of leaving it on binary search trees. You should be able to implement one. You don't have to worry about it being still terrible. We recognize it still could be terrible and end up like this. And we're going to run with that and decide that that's okay for right now until our next lecture set, when we talk about balancing trees, such as 2-3 trees, and another one that we'll see is ABL trees. All right, thanks everyone for joining me. Have a great day, and I'll see you in my next video.